On June 23, 2025, a single image went up on screens at the National Academy of Sciences in Washington, D.C., and within hours it was everywhere, shared across social media, splashed across news homepages, and downloaded by ordinary people who had never followed an astronomy story in their lives. It showed two glowing clouds of gas and dust, the Trifid Nebula and the Lagoon Nebula, rendered in a level of texture and color that looked less like a photograph and more like something painted. That single image, built from just over 7 hours of test observations, was only the opening act. Within the same release, a second image quietly contained an estimated 10 million galaxies, and almost nobody who shared it that day fully grasped that they were looking at a number that small, representing only a tiny fraction of what this same telescope now expects to eventually capture. This is the story of the day, the Vera C. Rubin Observatory's first images genuinely did break through into the public consciousness in a way astronomy releases almost never manage. And what has actually happened with this telescope in the year since? The event itself had been building toward this moment for nearly 30 years. The National Science Foundation and the Department of Energy's Office of Science had jointly funded the facility's construction. An investment exceeding $810 million and involving thousands of scientists and engineers across multiple decades. And the June 23rd reveal represented the first time any of that work had actually been shown to the general public in finished form. The event was live streamed in both English and Spanish, a deliberate choice reflecting the observatory's location in Chile and its intended global audience, and it was structured less like a typical academic press conference and more like a genuine unveiling, with speakers building anticipation before each new image appeared on screen for the first time. That structure mattered. Astronomy announcements are usually delivered as press releases accompanied by a single static image and a paragraph of caveats about statistical significance. This was staged deliberately as a moment, and the room's own reaction, audible gasps and applause captured on the live stream itself, became part of what made the footage worth sharing afterward, giving viewers watching from home a genuine sense of watching history happen in real time, rather than simply reading about a result after the fact. To understand why this particular release generated the kind of reaction it did, it helps to understand exactly what viewers were actually looking at, and why the numbers behind these images are so difficult to process intuitively. The Vera C. Rubin Observatory sits atop Cerro Pachon in Chile, built around an 8.4-meter telescope and the largest digital camera ever constructed, a car-sized instrument capturing 3,200 megapixels in a single exposure. Zeljko Ivezic, the mission's project scientist, explained during the reveal event that displaying just one of these images at full resolution would require 400 separate ultra-high-definition television screens arranged together, covering an area roughly the size of a basketball court. That specific detail, more than almost any other single fact released that day, was the one that spread fastest online. A genuinely intuitive, almost physical way to grasp just how much visual information was packed into a single photograph, considerably easier for a casual viewer to process than any raw number of megapixels or gigabytes ever could be. The camera itself captures light across 6 distinct filters, spanning wavelengths from the near ultraviolet through the visible spectrum and into the near infrared, and its field of view covers an area of sky equivalent to roughly 45 full moons in a single exposure, an extraordinarily wide angle of coverage for an instrument capable of this level of resolution. Each individual exposure lasts only about 30 seconds, and the observatory is designed to capture a new image at a pace of roughly 1 every 40 seconds throughout an entire night of operation, cycling through different patches of sky in a carefully choreographed pattern designed to cover the entire visible southern sky once every 3 to 4 nights. The images released on June 23rd were composites, built by digitally stacking hundreds, or in the case of the nebula image, more than 1,000 individual exposures on top of one another, a technique that allows faint, otherwise invisible detail to emerge clearly once enough accumulated light has been layered together, producing the kind of rich, textured color and depth that made these particular images so visually striking compared to a single, ordinary exposure. There's also something worth understanding about why these two specific subjects, glowing nebulae and a dense cluster of galaxies, were chosen as the centerpiece of this particular reveal, rather than some other, perhaps more scientifically significant but visually plainer target. Nebulae have long occupied a special place in public astronomy imagery, ever since the Hubble Space Telescope's own early images of similar star-forming clouds became some of the most widely recognized photographs in the history of the field. Rubin's version of that same kind of subject benefited from something Hubble's narrower field of view could never offer: the ability to capture the Trifid and Lagoon nebulae together in a single, wide, continuous frame, showing the broader context of the surrounding star field rather than a tightly cropped close-up. This wide field approach, combined with the sheer volume of stacked exposures feeding into the final image, produced a level of simultaneous scale and detail that immediately distinguished it from imagery audiences had already grown accustomed to seeing from other observatories. The image of the Virgo cluster, released that same day, carried its own kind of viral appeal, sweeping spiral galaxies, several caught visibly in the act of merging with one another, scattered across a single continuous field of view dense enough that casual viewers reported losing track of where to look first. Stephen Ritz, a professor at UC Santa Cruz involved in the mission, described the emotional core of what these images actually represented, noting that seeing this level of detail for the first time genuinely moved people in the room, scientists included, many of whom had spent years, in some cases decades, of their own careers working toward this exact moment. Vera Rubin, deputy director for the observatory's construction project, offered a description that itself became one of the more widely quoted lines from that day, calling Rubin Observatory truly a discovery machine, and stating plainly that it would enable astronomers to explore galaxies, stars in the Milky Way, and objects throughout the solar system, all in a genuinely new way. That specific phrase, discovery machine, captured something important about how this observatory was being positioned to the public. Not as a single instrument built to answer one narrow scientific question, but as a genuinely general-purpose tool for astronomical discovery across nearly every category of object in the sky simultaneously. Neil Brandt, an astronomy professor at Penn State involved in the mission, echoed this same framing in his own remarks around the reveal, describing how the combination of Rubin's enormous field of view, spanning roughly 45 times the size of the full moon in a single exposure, with its ability to repeatedly revisit the same patches of sky, would allow researchers to detect real-time changes across the sky and catch rare, fleeting events that narrower, more traditional telescopes would likely miss entirely. Christopher Stubbs, a Harvard physics professor who has been involved with the project since its earliest planning stages, has separately described the specific combination of the telescope's large aperture and wide field of view as making Rubin an unusually powerful discovery machine in its own right, capable of supporting research ranging from hunting potentially hazardous asteroids to observational cosmology, a description that helps explain why so many different corners of the astronomical community, planetary scientists, cosmologists, and researchers studying transient events alike were all paying close attention to this same single reveal. Part of what made this specific release resonate so far beyond the usual audience for astronomy news was the sheer, easily grasped scale of the numbers attached to it. In just over 10 hours of test observations, before the observatory's real mission had even formally begun, Rubin had already discovered 2,104 previously unknown asteroids, including 7 near-Earth objects confirmed to pose no danger to our planet. For comparison, every other observatory on Earth and in space combined typically discovers roughly 20,000 asteroids across an entire year. A brand new instrument, still in its testing phase, had matched a meaningful fraction of that entire annual global total in less than half a day, a statistic simple enough to explain in a single sentence and dramatic enough to travel well on its own, without needing much additional context to land with an audience that had never previously paid attention to asteroid surveys at all. This kind of easily digestible, directly comparable statistic turns out to matter enormously for whether a science story actually spreads beyond specialist audiences, and it is worth appreciating why. Most astronomical announcements involve numbers that are either too abstract to intuitively grasp, a redshift value, a statistical confidence level expressed in units of sigma, a distance measured in some multiple of light years, too large to visualize meaningfully, or too narrow in their apparent relevance to feel personally interesting to someone without a specific background in the field. The asteroid count did neither. It was a simple, whole number, directly comparable to a familiar annual total, and it carried an immediately understandable practical implication. More asteroids found means a safer, more thoroughly mapped solar system, precisely the kind of framing that requires no specialized background knowledge to understand and appreciate on its own terms. Michael Kratsios, director of the White House Office of Science and Technology Policy, addressed the room that day with language that itself became part of the story, admitting that these first exquisite images reminded everyone present of the true meaning of words like awe and wonder, and the genuine limits of ordinary language to properly describe them. That kind of unguarded, emotionally direct reaction from an official presenting a government-funded science project is, in itself, somewhat unusual, and it likely contributed to why so many people outside the usual astronomy audience felt genuinely compelled to actually watch the reveal footage rather than simply skim a headline about it. Underneath all of this public attention sits the observatory's actual, longer-term scientific purpose, one considerably less flashy than a single viral image, but arguably more significant to the field of astronomy itself. The facility is named after Vera Cooper Rubin, an astronomer who, working with Kent Ford in the 1970s, produced some of the strongest early observational evidence for the existence of dark matter, discovering that stars at the outer edges of galaxies were orbiting far too quickly to be explained by the gravity of visible matter alone. Rubin Observatory's full 10-year survey is specifically designed to extend that same basic line of investigation to a scale Rubin herself never had the technology to attempt, tracking how billions upon billions of galaxies are distributed throughout the universe, and how that distribution subtly shifts over the course of the survey in an effort to finally place meaningful constraints on both dark matter and its similarly mysterious cousin, dark energy, the force believed to be driving the universe's ongoing accelerated expansion. None of this made for viral video clips the way the nebula and galaxy cluster images did, but it represents the actual reason the observatory was funded and built in the first place, a decades-long scientific investment that the viral imagery of June 2025 served in effect as a highly compelling public introduction to. It is worth being honest and direct about exactly what happened in the time since that single viral day, because the observatory's story did not end once the initial wave of public attention faded, the way it does for many one-time science announcements that generate a brief burst of shares before fading entirely from public awareness. Rubin spent the following months completing a careful commissioning and operational readiness process, and during that same window in mid-2025, it identified more than 11,000 additional previously unknown asteroids in just 6 weeks of preliminary testing, including 33 near-Earth objects and 380 distant trans-Neptunian objects. Then, on February 24, 2026, the observatory activated its real-time alert system for the first time, issuing 800,000 individual alerts to astronomers around the world in a single night, each one flagging a newly detected change somewhere in the sky, a supernova, an asteroid, a flaring black hole. Once fully operational, this same system is expected to generate up to 7 million alerts every night, a volume of continuous, real-time astronomical information that no previous observatory has ever come close to producing, and one that required an entirely new supporting infrastructure of automated software and coordinated follow-up telescopes around the world, just to make practical use of it. On June 30th, 2026, the observatory formally began its complete 10-year legacy survey of space and time, now producing a new image roughly every 40 seconds, every clear night, continuously building what mission scientists describe as the greatest cosmic movie ever made. This steady, unglamorous progression, commissioning tests, alert system activation, formal survey launch, none of it generated anything close to the same scale of public attention as that single day in June of 2025. And that pattern itself says something useful about how the public actually engages with ongoing scientific projects. A single, beautifully composed image, released with genuine emotional buildup and easily understood comparative statistics, will reliably outperform even genuinely more significant technical milestones when it comes to capturing broad public attention. Simply because it requires no specialized background to appreciate immediately, that does not make the quieter, more technical milestones any less scientifically important. If anything, the 800,000 alerts issued in a single February night, or the formal survey launch at the end of June, represent considerably more consequential developments for the actual practice of astronomy than the visual spectacle of the original reveal, even though almost none of it traveled nearly as far across social media. So here is the honest picture behind the images that genuinely did spread everywhere in June of 2025. The reaction was not manufactured hype attached to an ordinary result. A telescope, capturing more detail in a single frame than 400 television screens could display, finding more asteroids in 10 hours than most surveys find in months, and doing it all during nothing more than a routine equipment test, was always going to be the kind of story that traveled beyond its usual audience. It did, and more than a year later, the actual survey those first images only hinted at is now fully underway, quietly producing a new photograph of the sky roughly every 40 seconds, every single night, continuing to build toward the 20 billion galaxies it is expected to eventually capture across its full 10-year mission. What makes this particular story worth revisiting now, more than a year after the original reveal, is not simply nostalgia for a viral moment that has since faded from most people's feeds. It is that the actual scientific payoff of everything those first images represented is only now genuinely beginning. The nebula and galaxy cluster photographs that spread across social media in June of 2025 were, by the observatory's own description, a small preview, a proof that the instrument worked exactly as intended, rather than the substantive scientific output the mission was actually built to produce. That substantive output, the systematic 10-year survey now generating a fresh image every 40 seconds, the real-time alert network already issuing hundreds of thousands of notifications in a single night, the slow, patient accumulation of data toward answering fundamental questions about dark matter and dark energy that Vera Rubin herself first raised half a century ago, is the part of this story that rarely generates the same kind of viral spread, precisely because it unfolds gradually, night after night, rather than arriving all at once in a single shareable burst. If you want to see what this observatory turns up next as its real survey continues, subscribe and turn on notifications. because the images that broke through in June of 2025 were only ever meant to be a preview, and the telescope has been working every clear night since, quietly building toward discoveries considerably larger than anything a single viral photograph could ever fully capture.